Welcome everyone again. As I said before, I am from Lenka Kosková-Čísková from Technical University in Liberec. And in the first talk, I was talking about how we use Zephyr in education. And this is related to our current research project. And it's focused on reducing the e-waste. So this is the green electronics, which I had in a title. So just shortly mention what the e-waste is. It's practically every non-working piece of hardware where is that PCB on. So it can be some non-working computer, mobile, tablet, but also a lot of household electronics, machinery components, parts of the cards, and a lot of other stuff. Actually, e-waste and its volume is a really serious problem. If you are talking about green and sustainable solutions, we are mostly focused on, let's say, the carbon footprints of stuff. But if we will able to survive the climate change, the waste is the second big issue we are facing. I have some numbers on the slides just for you to see that we expect to grow it even more and more. And the problem with, especially with the e-waste, is that it contains, it's absolutely toxic. It contains a lot of metals you don't want to have in the environment. And also it contains actually a lot of resources we would like to use again or to save them because especially in Europe, we are kind of short of it. It goes to all those precious metals and silver, copper, gold, whatever. But actually it's really hard to recycle. So we cannot produce more and more e-waste as we are used to. We probably, as a humanity, have changed, will have to change our economy to some kind of circular economy. The project I already mentioned is called ECON, which is the abbreviation for European Ecosystem for Green Electronics, and it's founded by CHIPS U initiative, which is actually part of Horizon. It's kind of joint undertaking with academia, research, and also the industry. We are 50 partners included in this project, and the research is ongoing, started already 2 years ago, and we shall finish our project in the middle of 2026. We have both industrial partners. We have ST Microelectronics on board, we have Siemens on board, we have the Bosch, and a lot of companies which are focusing on printing the integrated circuit or recycling the e-waste, and also a lot of research institutes or the universities. The general workflow of the research is focused on applying so-called 6R principles in the electronics production and design. And we at TUL are responsible for a dedicated task that we shall provide some kind of study how software design can support or ease those 6R principles to become reality in the electronics design. And we are also responsible for part of the group which designs the educational material for the future engineers, explaining some goals and design principles if you want to have the electronic sustainable. So to the principles, actually, if you ever have been interested in sustainable electronics design, you probably were facing some slide like this. Everyone loves to have some slides. A week ago, I was on some meeting in Madrid, and the people who came had from 5 to 12 hours. So in Econ, we have 6 of them. And they mean that if you want to reduce the EVIs, you probably can focus on reducing of the usage of the materials inside your design. Again, in the project, we have a lot of research related to it. People are trying to use plastics instead of the metals for the PCB boards. They are using the print inks. They are printing the inks. There is a lot of research and several practical use cases will come out of the project. Then again, the other important key where we shall focus when we are talking about reducing the e-waste and sustainable device is the reliability of the device itself, because if it's reliable, it can last longer, so you do not need to produce so big amount of devices if you can somehow use them, let's say, with a with long expected lifetime. It's also a good idea to repair the devices, but again, it's not as easy as it is said. I will discuss it later, because if you want to repair the devices, they must be properly designed. You must to distribute these spare parts. You must to have manuals, whatever. We can also talk about reusing parts of the device which cannot work anymore. We can keep the example from, I don't know, for example, the scrapyard for the car. So the car is not capable of running anymore, but you can still use some parts to repair another car. So I will comment what we can do with the software, especially with the Zephyr. In this case, when designing, refurbishing means that the device is not capable of providing the original function anymore, but you can maybe change the software equipment to at least keep it working somehow again, not throwing it away in short time, use it for longer time to reduce the e-waste. And recycling actually means that when the device itself is broken, we will try to extract as much materials as possible to reduce all the important metals and other materials which we can have inside the product. From the software perspective, we are not focusing on recycling, because when you are recycling, there is nothing which can run the software anymore. So, but for all these other now 5 Rs, I can provide you some general best practices. And for our project, we will, at the end of the project, I would like to come out with some demos. And as the demonstration platforms, we have selected Zephyr operating system for, let's say, the middle class electronics, and also embedded Linux and Yocto to demonstrate some best practices, which we have as the recommendations. So when talking about reducing, again, mostly this is about the material and the hardware design. In the research of my colleagues in project, mostly this is focused on proper design of PCB, reducing the PCB, maybe higher integration of the devices, etc. So there is nearly nothing to do with the software, but actually batteries are also a waste, which is toxic and contains a lot of precious materials we would like to keep working as much as possible. So power efficient design actually reduces the amount of e-waste dramatically, because less batteries needed means that less batteries are also thrown away. The reduce principle actually, Zephyr is kind of native in this field because it was designed to be power efficient. So again, just few general best practices when designing with Zephyr. Of course, that you shall avoid those active busy loops. So use sleeping instead of these busy wait kernels, and also use event-driven programming like the IR queues or the semaphores or working queues to have a queue of the external event and run the device only when it's absolutely needed. And the other big, nice, beautiful feature of Zephyr in this particular area is this power management subsystem. Again, just probably all of you know it already, that it's kind of two-layer stuff. We have this system PM, which selects the power state, and device PM, which selects or can suspend the peripherals. So again, we have a software framework which was designed to be low power and which can be heavily recommended for everyone who wants to save the batteries and think about the power consumption of the device. And of course, the power management subsystem is useful if you are designing properly. So this is actually something you nearly do not to implement in Zephyr because it was already done. You just need to teach to design properly the application to focus on the power consumption, even if it's actually maybe not the issue because I don't know, you're designing, let's say, the smartwatches such as I have on my hand, and you can say, okay, it's not so boring for the user to plug it to electricity every second day, they will do it. But actually, again, be power efficient means that the battery itself lasts longer, and so you became more, your product is more sustainable. Regarding the reliability, of course, the original idea is easy, that reliable devices, and actually the problem with the sustainable design in general is that it's mostly much more expensive to design, build such system and keep them alive and sell them to the customers. But actually power efficiency is something you definitely want to have, so it doesn't stop you. Regarding the reliability, this is kind of different situation because again, if we will understand the reliability from the point of view of, let's say, the certified high reliable device, then to become reliable this way, it's absolutely costly. Because you need to use expensive parts, you need to probably do some heavy testing and maybe even get certified, and everything makes your device at the end much more expensive and customer is not willing to pay for it. But actually, if you will just focus on, let's say, keeping the device in the field alive as long as possible to help it. So generally speaking, how software can help us. If we will be able to monitor and observe the device in the field and to collect proper diagnostics like the errors, maybe the core dumps, maybe measure the temperature to avoid overheating, or again, we can measure the battery status, whatever. It can help us to predict the service needs and maybe apply the service to the device sooner than later. And the device can happily live for years somewhere. Of course, it's also important to have software designed modularly, because again, if device is designed from the hardware perspective to be modular, then it's easy to do small repairs and it's easy to maintain it with the long-term perspective. I mean, if some module stops working because after 15 years it's too tired and wants to be retired, then you still maybe keep the rest of the device working, just exchange it part. And of course, if you have the modular hardware design, it must be supported from the software side. And again, I mean, mostly you need to have stable API. Probably you need to be versioning somehow to allow easily swap modules. Maybe have some prepared system for the configuration. Generally speaking, doesn't matter which type of software you are using. And of course, what comes shall come to your mind when we are talking about maybe remote observation and remote bug fixes or repairs. We need to be ready for secure in-field updates of the software. So again, probably you need a software framework which is ready for, let's say, the remote updates, signed binaries, maybe also have already some support for rollbacks, and maybe even some support for CVEs and patching them in the field. And of course, if you want to be fault tolerant, you shall also, when thinking about the long life, have some kind of additional pieces of software. So watchdogs are useful for the diagnostics, and also, for example, using the storages properly. So for flash storages, it's a good idea to think about some kind of file system which supports journaling and weir leveling, and also probably configuring the storage safely, again, to avoid destroying the storage by fragment writes to some particular part, because many times the storage cannot be replaced. So again, from the software perspective, we really need to think carefully how to write and where. So again, if we will take these, let's say, theoretical stuff to the Zephyr, okay, I would like to mention two important parts of the huge Zephyr API, which I will have in my demo to demonstrate it on some real piece of software and a real device. So what's great in Zephyr that we have that universal logging API, which can be used to create all those, is very helpful for observation and diagnostics, and with the MCU MGR, it's you can retrieve those diagnostics, analyze them somewhere, and you can also control what and how it's reported. And again, what's nice that you can download it via some serial interface, or you can use some wireless or the network interface, which is also available. And again, what's absolutely important from the software perspective, let's say regarding the modularity, again, it's kind of nature feature of Zephyr that you shall abstract it by the interface, not by the specific part you have, because it may be different during the time. So you need to have application talking to stable APIs and the drivers and modules implementing later on some hardware dependent stuff. And again, from the, let's say, available operating systems of the similar size and scope we have on the market, Zephyr is a perfect candidate because it was designed to be modular, and it already has plenty of kind of standardized subsystems. So the general best practice recommendation is that if the subsystem already exists, use it, and just do the device T, maybe low-level driver stuff, which you cannot get when working, or can get it hard, much more complicated way if you're using the free RTOS or some other RTOSes, or maybe even frameworks such as, I don't know, whatever, Arduino, STM, whatever. And if the particular subsystem is not ready, again, Zephyr provides you some kind of guidelines how to properly design drivers inside the driver model, which Zephyr has, which is pretty unique in this type of the real-time operating system. So public headers, tables, and device instances, etc. If you will do it, let's say the standard way, again, you are ready, and your device probably will be reliable and will be kind of repairable or fixable in the field. And of course, here comes another beautiful feature of the Zephyr, and it's the concept of using the device trees and keeping absolutely separated, let's say, the hardware abstraction for the application code. So thanks to device tree bindings and all the techniques we have around device trees, it makes kind of switching those modules much easier. And again, it's easier to repair the device in the field. And of course, just the general recommendation for the binding, it's a good idea to keep some name if you're designing your subsystem, some vendor neutral name to be ready for switching and checking by the compatible strings, the proper driver. When talking about the securing field updates, we have MCU boot, which actually in Zephyr supports signed binaries, and the IMG tool for signing those binaries. So again, you do not need to change so much your design workflow to support, let's say, those sustainability principles. So again, it doesn't cost you much money. You can have it from the software perspective, and you are ready for the situation where the industry will be able to apply those principles, let's say in some kind of circular electronics. Actually, it means if you are designing properly with Zephyr, you're ready. That's great. And regarding the fault tolerance, again, we have watchdogs, we have core dumps, we have a lot of other stuff available in Zephyr, which we can use to analyze what's going on in the system, if there is a fault for, let's say, the software bug fix or fixing the hardware. Regarding the data protection, again, we have this little fs, and also we can set the NVS storage, and this means that we have nearly completely atomic storage again, and it's absolutely crucial if you have some part of flash which is supposed to be used really for a long time when talking, let's say, in tens of years. Yeah, regarding the repairing, actually, the original idea is that if the hardware gets broken, we are repairing, not throwing it away. From software perspective, I mean, repairing is the same, like, is a very similar, like to have it reliable and long life living, because mostly the long life will probably need some smaller repairs. And here the key principle is, again, the modularity and really the proper abstract design and layering of your application, which can be easily done in Zephyr. So again, here comes the abstraction first, that your application logic, generally speaking, shall be completely abstracted from the hardware-related code, and you shall have the stable software interfaces. We know that we kind of struggle with this in Zephyr, but you can at least try to get it in your application code. And of course, theoretically speaking, it's a great idea to have hardware designed as, hardware as a configuration, not as a code. So to have it described, it's some kind of metadata, which are actually not code, just the hardware description, and we need the software updates and upgrades in the field. So again, for the abstraction, there is already done a lot in the Zephyr ecosystem. So maybe you are even doing it and not thinking about it. It's kind of natural here. From the hardware configurations, we have device tree overlays, aliases, chosens, whatever, and it really makes it easy to swap the modules, much easier compared when working again in FreeRTOS or when working in some similar like Threadix or whatever we can name more. The RTOS is here. You just mostly you just change the device tree, recompile the stuff, and it's working. And what's important that you're not touching the application code when changing the hardware modules mostly. And of course, again, to have the, let's say, the stable interfaces and the versioning, which is important, again, when you're repairing, to be able to, that in the future, the new hardware module will be able to communicate with your application. A good idea is use the APR version in your driver API, and you can use this build assert we have in Zephyr. And also, it's a good idea to tag your releases and use the Zephyr revision identification in your West manifest, just to be sure that you can reproduce the builds over the time. Because again, for the long time, long life and future repairs, we need to reproduce the builds. Let's say in longer time perspective than next Friday, we need to be able to reproduce the build, let's say in next maybe 10 years. What's nice that again Zephyr was designed to keep this feature and have this feature, so it is possible to rebuild still build the binaries designed for first versions of Zephyr. So it shall be again doable quite easily with no price, let's say in the development costs. Regarding the reusing, actually, uh, um, reusing is the reverse side of repairing, because we understand the repairing that we keep the MCU part, let's say, the microcontroller part or the central unit part, and we are replacing the modules. For reusing, we understand it that the microcontroller or the central computing part is not working anymore, but maybe some external modules are still working. Again, there is a lot of work for our colleagues who are dealing with the hardware, because you need to have those modules with some kind of standardized connectors or whatever. There is a lot, and you have to distribute it, and you have to motivate the customers really to want to have those repairs. But from the software perspective, if you are ready for repair, you are also ready for reuse. So we really do not need to repeat anything here. We could just switch to the other slide where everything was already mentioned. Regarding the refurbishing, again, the device, from the hardware perspective, device is still working, but for some reasons, its original function is kind of not interesting anymore, or it cannot do its original function. I have two examples, one of them, and mostly it comes from, let's say, the computers with the universal operating systems. So we were facing this situation, let's say, a year or two ago, when the Windows 11 were released. There are plenty of laptops in the world which were labeled like not ready for Windows 11, but actually those laptops are still working. So refurbishing means that you are using it again, but with different software equipment. And the same, we have a use case in the research project that there is a group of people who are demonstrating that the old mobiles can be still used, for example, as routers or some edge devices working at the edge for the Internet of Things, whatever. I mean, the device itself is not supported anymore by the Android operating system provider, but the hardware is working, so let's use it. There is no specific command in Zephyr. I mean, when you are able to flash the code to device, you are simply using it. And so we don't need to provide any command. I mean, it's a software who does the refurbishing. So if you are able to build binaries and run them, then it's okay. And it's mostly depending on the hardware configuration you have. So if I will conclude what I presented, if you actually do the professional design with Zephyr, luckily, you are kind of sustainable, because probably your design is ready for all the circular economics principles, which probably will be sooner or later implemented, especially in Europe, for the electronics, because all what can be done from the software perspective is already somehow available in Zephyr, or maybe you are even doing it already. You just didn't know you were green and sustainable. So well-designed, because the well-designed Zephyr application is immediately modular, and it's reliable, and it's power efficient, and it's upgradable. So you nearly do not need to add some subsystem, API, library, whatever. You just need to orchestrate it all together, and it's done. So this is the reason why, again, I have selected Zephyr to demonstrate those recommendations, and because it's the best choice you can do if you are thinking about those ideas when designing your devices. Okay, so that's all from my side. I'm open to question, which maybe I can hear now. I don't know.
So thank you very much for your insights. How can we build better devices or greener devices? You can clap, of course. But you also can ask questions to Lenka. So is there any question here in the audience? or sleeping.
So thanks for the interesting talk. I was wondering if we look at the second bullet point, isn't basically any application that's modular, reliable, and long-living and power efficient well-designed? Or the other way around, isn't any well-designed application modular, reliable, and so on? What's specific to Zephyr in this statement?
I mean that, yeah, what's specific to Zephyr? I mean that Zephyr was designed and written for you to do these types of design if you are using it properly. We discussed already the Arduino. So actually, when you are designing with Arduino, you are starting with a busy loop, and you are absolutely not power efficient, mostly, with the Arduino design. And again, this is when using the Arduino framework, a lot of stuff is now hardware dependent. You have low power states, which are available for some architectures, but some of them, they are not available. You don't have this nice, let's say, power management subsystem, which kind of covers it all. So you are doing the research again and again and again. And if it's not, I mean, your main design goal, then it's problem. Regarding this reliability or long life, again, in the other real-time operating systems, it's sometimes pretty complicated, for example, to do the infield updates with signed binaries. Sometimes it's implemented, sometimes it's not. Or to do, I mean, the observations. What's nice in Zephyr is that it doesn't matter which type of hardware you're using, and you already have those interfaces. But actually, no one wants to design an unreliable device. Yes. You just can emphasize it in your design if you're interested. And Zephyr makes it easy for you.
Okay, thank you. Any more questions here? Doesn't seem so. Okay, thank you, Lenka, very much for your talk. And we are switching back.